This is a short dedication to Professor Kunii and how the intersection of our lives changed my trajectory in academia. When I discovered computer graphics as a fledgling doctoral student in the 80s, Professor Kunii was already a leader in computer graphics. And I remember reading his books and papers with awe. At that time, I was a graduate student, a doctoral student in physics, similar to Professor Kunii's early career in physical chemistry. And I was looking for something with a more visceral connection to the real world. And Professor Kunii's papers, and especially his books, opened my eyes. And his inspiration was one of the factors that contributed to me switching my career path toward computer graphics. My first personal connection with Professor Kunii occurred when I was involved in organizing a relatively new conference, Pacific Graphics, in the mid-1990s. Being a fresh PhD with no experience in organizing conferences, Professor Kunii provided wisdom and experience that helped us immensely, despite the great differences in our stature in the graphics world. Professor Kunii was very warm, approachable, and showed genuine interest in our new conference. And I'm forever grateful for his warm smile, quiet confidence, and deep humility. This paper, I believe, is particularly appropriate for this homage to Professor Kunii. Technically, one of the main thrusts of his research in the mid-80s was ray tracing CSG and octree data structure, which we reference actually in our paper. Our paper is a bridge between those early work and the modern volumetric ray tracing, made especially relevant by the advent of dense scene capture using optical scanning technology. This paper is primarily the work of one of my newest doctoral students, Wei Li. And the legacy of Professor Kunii lives on through our students. Thank you.
In this presentation, we propose an efficient grid-based raycasting method for rendering polygonized isosurfaces of binary volumes. Voxel-based modeling or voxel art has become a popular trend recently due to the development of digital sculpting devices and software. It allows users to directly modify solid objects with simple primitives and Boolean operations, thus removing the complexity of manipulating geometric topology and texture mapping. Media material attributes can also be stored with voxels to support light transmission, which is difficult to be implemented with meshes only. Binary volume is one of the widely used data structures for voxel-based modeling. It is a special discrete sampled scalar fields, where the value at each uniform grid can be either 1 or 0. The dataset can be sparse or dense, depending on how the dataset is generated. Besides handcrafted by users in sculpting software, the binary volume can be generated from other primitives, quantization of scalar field or procedural algorithms. The most straightforward way to visualize binary volumes is to render each solid voxel as a simple cube. However, the blocky surfaces and contours are not always appealing to users. Another method is to directly raycast the trilinear interpolated isosurface for a smoother visualization. This leads to a root-finding problem of a cubic or an even higher degree equation which involves expensive computation and numerical errors. The uneven surface is also not appropriate in certain cases where flat surfaces are preferred. Another category of rendering methods is to approximate the isosurface by polygonizations, such as marching cubes. It replaces the right-angle edges of cubic voxels with 45-degree flat bevels, making it a popular rendering style in voxel art community. In this paper, we choose the polygonization as our rendering style for binary volumes and propose an efficient grid-based raycasting method for it. The examples shown in the previous slides are rendered by the proposed algorithm. In our method, the polygonized isosurface of binary volumes is directly rendered by a two-stage raycasting algorithm, thus no polygon conversion or rasterization is involved. In the first stage, The ray traverses through the uniform grids and skips empty cells until the ray encounters a solid cell containing the surface. We use an auxiliary structure, the region index layer, to adaptively leap empty regions of the uniform grid. Then we switch to the second stage to calculate the nearest intersection point on the interior planes. We use Boolean combinations of half-space subvolumes to represent the surface to reduce the cost of intersection tests. In previous works of grid traversal, 3D DDA and FVT can traverse the uniform grid cell by cell with simple instructions, but it takes lots of steps to leap large empty space. Hierarchical data structures such as octree are then applied to exploit the spatial sparsity of voxel data to reduce the storage and traversal cost. There are also other variants such as gigavoxels which have varying and wider branch factors for different levels to decrease the tree depth. However, the memory consumption of pointers and the stack-based traversal make them less efficient for dense and complex scenes. Therefore, we apply a multi-level data structure called region index layer to skip empty regions as efficiently as octrees, but with simpler traversal steps as 3D DDA. A region index layer is of uniform grid which corresponds to a flattened octree. The region index indicates the depth of an empty subtree. With this information, we can keep traversing horizontally at the bottom level to skip the empty subtrees without vertical movements along the internal nodes in an octree. To efficiently evaluate the region index, we assign each 8x8x8 tile a workgroup and evaluate the region index value in the local memory. When the calculation of a finer layer is finished, we initialize the region index to 0 for totally empty regions at a coarser level and repeat the process. Then the final region index can be calculated as the maximum value through all the layers. This table shows the storage and evaluation costs of the region index layer at different resolutions. It consumes about 12% less memory than that of a complete MIP map. These figures visualize the number of iterations for the primary rays. Pure while color corresponds to 128 iterations. As can be seen, the region index layer requires fewer horizontal and vertical movements than that of 3D DDA and octree. For quantitative comparison, region index layer-based traversal spends around 40% less time than that of octree-based traversal and around 80% less time than that of 3D DDA. When we find a solid cell in the grid traversal, we check whether there is any intersection with the polygonized isosurface within the cell. Here we use marching cubes as our polygonization method. In marching cubes, there are 256 cube configurations in total. The figure illustrates the 18 basis configurations, while the others can be obtained by rotation and complement transform. Instead of representing the surfaces by triangles, we represent the cube configurations by half-space subvolumes, which are called basic primitives. For example, case 1, 2, and 9 can be all represented by a single basic primitive, though they have different numbers of edges. To raycast the basic primitive, we compute the entry and exit depths to evaluate the ray interval within the solid object. An intersection point exists when the ray interval is invalid interval. A compound primitive can be constructed by Boolean combinations of several basic primitives. As shown in the figure, different triangulations lead to different Boolean combinations. And more triangles lead to more complicated Boolean combinations which may increase the branch divergence. For example, case 3C only needs one union operation, while case 11 needs one intersection operation followed by one union operation. Note that the triangulation is not unique. Some can produce simpler combination sequences without breaking the topology consistency. And the triangulation is also special. All the vertices and ridge edges are located on the boundary of the cells. So if we construct a convex hull from the vertices and edges, the vertices and edges must always be part of the convex hull. This leads to our solution. We can generate the interior triangles on the convex hull so that all the intersection operations can be replaced with union operations to simplify our computation. To raycast the compound primitives, we compute the ray intervals and combine them based on the operations shown in the table. To avoid any missing inner intersection points for concave shapes, we must perform Boolean operations in the complement intersection union order. For example, for complementary cases, we need to apply an additional complement operation after the union operations. Therefore, we need to apply distributive and De Morgan's laws to expand the expressions. In contrast, in triangle representation, the watertight ray triangle intersection performs the edge tests on a transformed 2D plane. It requires 6 multiplications to swizzle, scale, and shear vertices, 6 multiplications to compute the scaled barycentric coordinates, and 6 multiplications on 1 division to calculate the hit depth, but in the CSG representation, we only need 6 multiplications and 1 division to calculate the hit depth on the plane for each ray interval. This is because that the boundary edge tests are addressed by the intersection between the ray and the cell. The inner edge tests are addressed by the Boolean combinations of the basic primitives, and the edge tests on the coplanar planes are reduced. Here is the comparison for the storage between mesh and volumetric representation. Since the volumes generated by the users can be very dense and noisy, we use randomly generated binary volumes as the worst cases. As can be seen, at higher resolution, the mesh extraction consumes too much memory, even without any acceleration structure. While in the volumetric representation, we only need to store 1 byte for the index of cube configuration and 1 byte for the region index. Here is the comparison of the ray intersection performance for each basis configuration. We sampled random rays through the unit cube and evaluate the average performance. As can be seen, with the reduced edge tests, ray CSG intersection test spends at least 45% less time than that of ray triangle intersection test within each cell. Thank you for your attention.